Okay, continuing with this page, talking about general issues with acids and bases. The next thing we want to think about is what's called the self-ionization of water, and how this relates to the pH scale, which is how we measure the strength of the acidity or basicity of solutions. Self-ionization of water sometimes is called auto-ionization of water, and I went ahead and wrote in this reaction in between videos here. So in a sample of pure water, this can happen. One water molecule, in this case, can act as an acid, donating a proton. Another molecule of water may act as a base and accept that proton. So that would give us hydronium ion and hydroxide ion. This, of course, is reversible. That proton could transfer back. We can think about what is the equilibrium constant for this reaction, and there's a little subscript W on there. This is called Kw. We'll see this is going to be an important way we can relate some of the properties of acid-base solutions. Pure liquid water on the reactant side of the equation means we won't have any denominator in this equilibrium constant. So we'll just have the contribution of the products. So this is the hydronium ion concentration times the hydroxide ion concentration. Now, at 25 degrees Celsius, there is a set value for Kw, and it is 1 times 10 to the minus 14th. Now, this does vary a little bit with temperature, but for general purposes, this is the value we will use for aqueous solutions. Right? So under normal pressures, aqueous solutions only exist between 0 and 100 degrees C. So this is a pretty good approximation, even if we do deviate from 25 degrees Celsius for our temperature. Now, if we solve here, in pure water, right, so take the square root of 1 times 10 to the minus 14th, the concentration of hydronium ion in pure water is equal to the concentration of hydroxide ion in pure water, and that's equal to 1.0 times 10 to the minus 7th molar. So pure water has this concentration of hydronium and hydroxide ion. These ions are the basis of the pH scale. So the definition of pH is it's the negative base 10 log of the concentration of hydronium ions in a particular solution. Okay, so in this case, if we plug in 1 times 10 to the minus 7th, we take the log of that, base 10 log, then we change the sign, the pH here would be 7. So pH 7 is what we would call a neutral solution. Now, if the concentration of hydronium ions was to go up, then that would give us a solution that would have a lower value for pH, and that is something we would call acidic. So if the pH is less than 7, that's an acidic solution. And if the pH is greater than 7, that is what we would call a basic solution. But since these two quantities are related in this particular equilibrium constant expression for pure water, and if we know one of these components, we can always figure out the other one. If we know the hydronium ion concentration, we can calculate the hydroxide ion concentration because we know Kw, and vice versa. If we know hydroxide and Kw, we can calculate hydronium ion. So since these are related, we can figure these out for any solution we might encounter. And that's something we'll have to look at as we get into kind of the more complicated problems here that involve weak acid and weak base equilibrium. So a couple examples down here, just comparing hydronium and hydroxide ion concentrations and calculating pH. Right, so the directions here indicate whether solutions with each of the following ion concentrations are neutral, acidic, or basic. The way we're going to do that is by actually calculating the pH for each of these solutions. So if we look at the first one, the hydronium ion concentration is 4 times 10 to the minus 9th. Well, that means the pH here is going to be the negative base 10 log of 4 times 10 to the minus 9th. So if I plug that into my trusty calculator, negative base 10 log 4 times 10 to the minus 9th, execute that, 8.3979. So let's round that to 8.4. So that's the pH of this solution, 8.4. So this pH is a little bit basic, right? If the concentration of hydronium dips below 10 to the minus 7th, that means the concentration of hydroxide ions goes above 10 to the minus 7th, and that would be a solution with a little more base than acid. Now, sig figs are a little weird when logs are involved. Essentially, however many sig figs you have here in your concentration is how many you should have after the decimal in your pH. So the number to the left of the decimal comes from the exponent here. The number to the right of the decimal comes from the value here at the front of your scientific notation for your concentration. So if this is one significant figure, you have 0.1 place. If this is 2, you'd have 0.2 places. Okay, so what you really want to be careful of is not over rounding your pHs and losing a lot of information. Okay, the second one here, hydroxide ion, is 1 times 10 to the minus 7th. Now, that's maybe a little too straightforward because we just did that calculation. If the hydroxide ion concentration is 1 times 10 to the minus 7th, so is the hydronium ion concentration. That means the pH here is the negative log of 1 times 10 to the minus 7th, which would be 7.0 for a neutral solution. The last one, so acidic here for the first one, neutral here for the second one. Now this last one, we're given the hydroxide ion concentration, 7 times 10 to the minus 13th. Now here's where we can think about how we can use Kw. Because to get pH, we need hydronium ion concentration. So if I take my Kw expression up here, I can rearrange that to solve for the hydronium ion concentration. Excuse me, a little sneeze action there. So if I move hydroxide ion concentration to this side of the equation, that would be Kw over the hydroxide ion concentration. Kw is 1 times 10 to the minus 14th. The hydroxide ion concentration we were given is 7 times 10 to the minus 13th. Okay, if we plug that into the calculator, we get 0.0143 molar. That would be the hydronium ion concentration in this particular solution. That means we can take that concentration, plug it into the equation for calculating pH, right? And that gives us a pH of 1.8 for this particular solution.